Hey guys, welcome to another IGCSE physics video. Today we're going to be going through the first part of electrical quantities. So this is the syllabus content that we're going to be focusing on this video, and the next video will be covering the rest of the things covered in this particular topic. But we'll be looking at 4.2.1, which is about electric charge, static electricity, field lines, and all that stuff. So the first thing we'll do is just sort of talk about conductors and insulators. It's very simple. A conductor is something that sort of allows electric current to flow through it freely. An insulator, on the other hand, prevents any sort of electric current flowing through it or is fairly resistant to it. So the reason why conductors allow electric current to flow through it very easily is because it's got free flowing electrons that allow it to happen. And so therefore, a good conductor, metals for example, are really good conductors because if you have taken chemistry, you know that metals have free electrons throughout the structure, metallic bonding. But if you don't know chemistry, that's fine. Just be aware that metals have free mobile electrons, so electrons that can move around throughout the structure in it to allow the passage of electric current through it. Insulators, on the other hand, do not have any free electrons that are able to sort of move throughout the structure. They're usually very tightly bound in the atoms of the insulator. So because they're not free to move, they do not allow the passage of electric current through the structure, and that is what that's what gives it its insulating properties. For example, rubber is an example of a good insulator. So let's talk about electric charge, right? Electric charge is defined as the physical property of matter that causes it to experience a force when placed in an electromagnetic field. The unit for charge is coulombs, and we'll talk more about that in the next video. But for now, just be aware that this is the formal definition of an electric charge, fairly self-explanatory, so you should definitely learn it. Of course, you may already be aware that there can be positive charges and negative charges. And the main thing that you have to be aware of is how they interact with each other. Opposite charges will always attract, sort of like opposite poles of a magnetic sort of a magnet attract each other. And like charges repel, sort of like how like poles repel in a magnet. So here is a diagrammatic representation of that. You have two like charges, positive and positive and negative and negative. They will always go away from each other because they repel. Opposite charges, however, for example, positive and negative, they will attract. Therefore, you've got these direction, the direction of these arrows here. So now that we've looked at an electric charge, which of course by definition, if you look over here, it experiences a force when placed in a electromagnetic field. Naturally, we're going to be looking at electric fields, which is defined as a region around an electric charge where another charge experiences a force, and that is an electric field. So field lines basically show the direction of a positive charge, the direction a positive charge would move if placed in the particular field. So we are thinking about everything in terms of field lines and things like that in perspective of a positive charge. So first of all, we're going to be looking at point charges, which is a charge at a single point. If you have a positive charge at this particular single point, you have electric field lines radiating out from the positive charge, because remember, the field lines go in the direction where a positive charge would move if placed in the field, right? So a electric charge from an isolated positive charge will have the direction radiating outwards. In comparison, a point charge of a negative charge will have field lines that go towards it, because again, if a positive charge were to be placed anywhere here, you'd expect it to go inwards, because again, attraction lies between opposite charges. So you should memorize these two diagrams here. Pretty simple. If it's a positive charge, the electric field lines will radiate out. If it's a negative charge, it radiates inwards. the electric field lines between two parallel plates, again, it depends on which one's positive and which one's negative. You see this top plate here is positive in this instance, and so because we are drawing the arrows in the direction that a positive charge would move across the field, then you'd expect, if you put a positive charge anywhere on this field here, you'd expect it to go down towards the negative charge, because again, opposite charges attract, right? So we're going to draw the field lines like this. They are fairly uniform, they're straight, and they go straight from the first plate to the second plate in this instance. But if the positive was the other way around, right, if the bottom plate was a positive and the top plate was a negative, then the direction of the arrows would be completely reversed. So charging a body basically involves the addition or removal of electrons, and that is a fundamental key that you need to be aware of. If we're going to be charging something, we're basically giving it some sort of electricity, right? We can either charge it to become positive, we can either charge it to become negative, but in the core of all that, the reason why something becomes charged is because it either gains or it removes or it loses electrons in the process, right? So there are three main ways we can charge a body. You can charge it by friction, conduction, and induction, but for your course, you really only need to know friction and conduction. So let's take a look at charging by friction, right? So as the name would suggest, friction is basically the idea that you rub two things together to give each of those two things charge. And to understand this concept, you need to be aware that different materials are obviously made of different atoms and things like that, but because of the differences in the properties of the atoms that the material is made of, each material has a different electron affinity. And electron affinity is basically the amount of love or how much it attracts electrons. The larger the electron affinity of a certain material, the more love it has for electrons and the more it sort of attracts electrons, compared to another material that has less electron affinity, suggesting that it has less love for electrons and it doesn't attract electrons as much, right? So when an object is rubbed over another object, the electrons will get transferred from one object to another due to this friction. And the reason why it moves is because these two materials have different electron affinities, right? So the electrons, as you rub them, as you rub the two materials, the electrons will move from the material of lower electron affinity to the material with higher electron affinity, because the higher electron affinity material attracts electrons more, so it basically steals electrons from the other material. So the object that loses electrons becomes positively charged, because if we think of a material as neutral, suggesting that there's equal positive and negative charge, if it's overall losing electrons, then it's going to become positively charged, right? And oppositely, the object that gains or accepts electrons becomes negatively charged, because again, if an object is neutral and it just gains some electrons, then there's more negative than positives now, so overall it has a negative charge. So one really key aspect of this is that it only works for insulators, because basically what it is we took a look at the definition of insulators and conductors before, right? And so conductors always have free-flowing electrons throughout the structure, and this concept of friction and charging by friction only works for insulators because when electrons get transferred from one object to another, because insulators don't have the capacity to redistribute electrons, because the electrons throughout the structure are not mobile or they cannot be moved, the electrons that get added on or lost, basically, they don't get redistributed, so you have a localized charge. But in metals, right, you create friction with two metals, and one, let's just say electrons get transferred from one metal to another. Theoretically, when that electron gets transferred to the other, then that would make the object that gains the electron negatively charged, as we talked about before. But in a metal, that doesn't necessarily happen, because as soon as the electrons get added onto the metal, it gets redistributed immediately and it basically gets discharged. Right, so you don't have to dig too deep into this, but just be aware, by friction, you can only do this with insulators, simply because electrons do not move throughout the structure and they do not get redistributed, so that allows objects to gain and lose, or will basically gain charge. So if you take a look at this particular diagram on the right, you can sort of diagrammatically exemplify what's going on, because you've got two insulators, you've got a glass rod and you've got silk cloth. If you rub these two together, what will end up happening, is that you'll get a net charge of the glass rod being positive and the cloth being negative at the end of sort of rubbing them together, and so therefore you'll get that attraction between these two materials because now they're technically oppositely charged. So if you think about it, which material here has the higher electron affinity? It must be the cloth, because ultimately what has happened is the electrons have moved from the glass rod, it's been donated to the cloth, and that allows the cloth to be overall more negatively charged now because it gained electrons, whereas the rod, because it's lost electrons, it is positively charged. So that is charging by friction. If we look at charging by induction, this is probably the most important for your course. The process of charging the uncharged or charging an uncharged object by bringing another charged object near to it, but not as to touch it, is called charging by induction, right? So you bring a charged object, for example this plastic rod that has a negative charge overall, you bring it close to this metal conducting sphere, which is overall neutral. It's got the same amount of positive charge at it as it does with negative charge, right? So overall the sphere is neutral at this point, but if you bring the plastic rod near it, because you know that like charges repel and opposite charges attract, what you'll get is the polarization of this sphere, because all the positive charges inside the sphere will get attracted towards the rod, in this case towards the left hand side, and all the negative charges will actually get repelled and move over to the right hand side. So you get a split, right? All the positive charges on the left hand side, all the negative charges on the right hand side. Now if you were to then connect a wire to the ground and you connect it to the right hand side here, because if you think about it locally, if you just think about the region on the right hand side, you have a huge amount of negative charge, right? There's an excess of electrons here. It's crowded with electrons basically, and it's not usually electrons don't prefer to be crowded like that. So what happens when you have a crowded amount of electrons like so? The electrons will move out of the sphere through the wire into the ground. Now, the ground is simply a large object that serves as almost an infinite source of electrons or sink for electrons, right? So if it was the other way around and there was a deficiency of electrons over here, then you'd actually get electrons moving into the sphere. But because we have an excess amount of electrons, specifically in this region here, we're not talking about the whole sphere, we're specifically looking at this half here, you know that there is a crowding of electrons. So because of that, electrons will move out of the sphere and into the ground. And basically, a ground contains such a vast space that it is basically the ideal object to either receive electrons or supply electrons to whatever object that needs to get rid of them or receive them. But again, that probably isn't something that you need to dig too deep into, but be aware that electrons will move out of the sphere towards the ground. So ultimately, if you were to account for that, what you'll be left with is an overall positive charge after the electron leaves the sphere. So you basically induced charge or induced positive charge in the sphere by using this method. Now, it doesn't necessarily have to be a wire that leads it to the ground here. You can actually simply touch the sphere on the right hand side here, and you as a person and your skin can actually act as something that can sort of conduct the electrons and receive the electrons and lead it to the ground. Okay, so this is exactly what we'll be looking at in this diagram here. So in the diagram on the right, if you take a look at the top series of diagrams, this is exactly what we did on the left hand side here, exactly the same. What you do is get a negative charged, they use the balloon here instead of a rod, but it doesn't matter, negative charged balloon, and all the positive charge accumulates on the left hand side, all the negative charge accumulates on the right hand side, and so therefore when you touch the sphere, the electrons will move out of the right hand side and enter the ground. And so if you get rid of your hand from the sphere now, the sphere is overall charged positively with excess charge attracted to the balloon. You get rid of the balloon, then you get the positive charge evenly distributing itself across the sphere, which is exactly what happened over here. When you remove the rod from, near the sphere, the positive charge sort of redistributes itself and scatters itself across the sphere. But what if we did everything the other way around, and instead of a negative rod, or here, instead of a negative balloon, we use a positive balloon to induce charge? What will happen? So let's take a look. Exactly the same process, but sort of the other way around. You have a positive charge near the sphere, then all the negative charges will actually get attracted towards the left-hand side of the sphere now, naturally, due to the attractive forces, and the positive charges will repel towards the right-hand side. You have the polarization of the sphere, suggesting that one half is sort of negative or accumulation of negative charge, the other is an accumulation of positive charge, right? So then again, if you were to just place your hand on the right hand side of the sphere there, the electrons will basically not leave the sphere, but it will come into the sphere this time, right? Because think about it this way. If you, on the right hand side here, there is an accumulation of positive charge. An accumulation of positive charge is exactly the same as a deficiency of negative charge. So you could say that because it's so positive here, there is a lack of electrons. And remember, the ground is basically something that has an unlimited amount of electrons, right? That can act to donate electrons when needed. So if you think about it, here is, and on the right hand side here, there's an accumulation of positive charge. So the ground supplies electrons to the sphere, so electrons actually move into the sphere this time. And so basically the electrons move in because they're attracted to the positive charge, and so the sphere now has an excess of electrons, given that the electrons have now entered into the sphere from the ground. And if you get rid of the balloon, then the electrons or the negative charge will distribute itself across the sphere just like so. So if you use a positive rod or a positive balloon to induce the charge, you'll induce a negative charge. If you use a negative balloon or a negative rod to induce the charge on the sphere, you'll actually get a induced positive charge. So those are pretty important concepts that you need to know, but I do think that if you just take it step by step, it is a pretty simple concept to follow. Now, you see that these spheres have an overall charge of, up here is a positive, down here is a negative. And if you were to draw the field lines for these spheres, it would look very, very similar to that of what we looked at for a point charge. So go back to the field lines of a point charge and you'll see what I mean. And that would sort of be how it looks like if you were to draw out the field lines for these conducting spheres. Okay, so that is it for today, guys. Thank you so much for watching. Please do like, share, and subscribe. It does really help the channel. And please check out Patreon for exclusive past paper tutorials. I haven't done any for physics yet, but do have a look because there is quite a lot for chemistry and bio. I am still uploading chemistry, but without further ado, I think I will end this video, and I will see you in the next video. Cheers.